Hello everyone. Today's lecture we will continue integrated optical components of course, and we have discussed directional coupler in the last lecture. Coupled waveguide, basically we constructed differential equation, two coupled equations between guided modes in either waveguides. Now, starting from that differential equations, coupled differential equation, we will try to solve the power coupling between the two coupled waveguides. And finally, I will discuss about how to formulate a transfer matrix, because this transfer matrix is the one one can use for circuit simulations, because directional coupler is an important component for photonic integrated circuit. It is used for many circuit demonstrations. So, it is an important circuit element. So, for circuit simulation, this transfer matrix is a very important formalism, and we will be discussing that. All right. So, to solve coupled differential equation, we just recap a bit how we got the coupled differential equation. We consider two waveguides. They are parallel waveguides, waveguide A and waveguide B, and this is a representative waveguide structure in silicon on insulator, and Na square xy is the refractive index distribution to define waveguide A, n square b xy, that is corresponding to waveguide B. And individually, if you solve, the mode field distribution, dominant electric field distribution is EAxy for waveguide A and EBxy for waveguide B. And the eigenvalue propagation constant for waveguide A is beta A and waveguide B is beta B. And we should keep in mind that this beta A and beta B we are calculating for same frequency, that is beta A equal to omega by C, n effective for waveguide A, and beta B equal to omega by C, n effective B. So, if we do not consider that these two waveguides are identical, that means non-identical waveguide, then obviously beta A not equal to beta B, obviously EAxy will not be equivalent to EBxy, their distribution may be different, okay, and that can be due to waveguide dimensional variation. One is WA not equal to WB, waveguide width. Obviously, device layer thickness, it is considered same, HA, HB, but the what you call that, this is your slab height. Slab height you can vary also. This side waveguide A, you can have a slab waveguide A, this can be also not equal to, can be not equal or can be identical. One of them can be not equal, and in that case beta A not equal to beta B. And we know that when they are coupled, we cannot really consider that amplitude of electric field distribution that is propagating through the waveguide A will not be constant, that will have some kind of slowly varying amplitude AZ in waveguide A, slowly varying amplitude. We will be considering that the presence of waveguide B is weakly influencing the guided mode what is there in the waveguide A, and this is vice versa. This is the waveguide mode B, which is slightly or weakly influenced by presence of waveguide A, and that amplitude will be slowly varying as a function of Z, slowly varying, right. So, this is actually your total field, we can say, for the system of coupled waveguide, which is defined by this type of refractive index profile, we have discussed in the previous lecture, and if this is the refractive index profile, we can say that okay, they are superposition of slowly varying field amplitudes in waveguide A and waveguide B. This is the two things. This is your total electric field. Okay. This is what we can just we have considered to construct the coupled differential equation, which is nothing but this one and this one. So, basically this A and B, how they are coupled, that actually will define the power or amplitude component or presence in waveguide A and waveguide B. Okay. So, this is something the first term and this is second term. The first term you will note we have kappa AA and it is AZ. That means, evolution of mode A in waveguide A, amplitude A, because of some kind of coupling coefficient kappa AA in that waveguide itself. So, that is AZ, because something contribution or can be considered as a somehow this term related to its own perturbation in waveguide A. Similarly, this one here also you see this one, but this is the term actually coupled term, that is actually this term. If this is non-zero, that means something from waveguide B is being contributed to waveguide A. Similarly, here if you see whatever it is there, same way we can consider waveguide B amplitude will be evolved because of the presence of waveguide A, amplitude AZ. So, this is basically second term is the coupled coupling terms, that power energy can transfer from one waveguide to another waveguide. Okay. So, this is the coupled equation between two waveguide modes we have derived earlier in the previous lecture. We just put down here to follow up. Okay. Now, if you see this kappa AA, that is what I said that in our coupled mode equation when we derived, we found that that expression is looking like this, where this is like a coupling strength though, but you see EA star and delta NB square presents in the integration. That means, we say that disturbance term of the guided mode in A, waveguide A, due to the presence of delta NB square, due to the presence of waveguide B. So, if this delta NB if equal to 0, then kappa AA would have been equal to 0. That means, something contributing that presence of, because evanescent tail is actually from waveguide A, it is penetrating to waveguide B. That is why this delta NB square, the presence of second waveguide will disturb the waveguide mode in waveguide A. Same way for kappa BB, this term and this term is defined like that. We assume that these two terms, once we know the field distribution in waveguide B and waveguide A, where individually they are simulated using your full vectorial solutions or whatever mode solver you use, and once you solve that and once you know delta NB square and delta NA square, the vicinity where the waveguide A and waveguide B they are mutually interacting, then you will be able to compute these two. So, we can assume that this kappa AA, kappa BB can be computed once you know the waveguide profile, that means once you know this refractive index profile. Okay. So, now note, this is the important thing, kappa AA equal to delta beta A, kappa BB equal to delta beta B, because you see this is the term actually disturbed waveguide mode because of the presence of the waveguide B. So, how it is disturbed? It can be shown that is actually the value actually is nothing but your propagation constant of beta A will be modified as kappa A. That means, if you just treat that how the phase of the field in waveguide A, how that will be changing as a function of length, that is actually propagation constant, that you can actually consider like that. If there was no waveguide, second waveguide, then propagation constant was beta A, but presence of second waveguide, this kappa A will be adding. Same is true for here. So, beta B should be added with kappa BB. We will show very quickly how that is feasible very clearly. So, we can say that this kappa BB is equal to delta beta b, that is what I have written here, and kappa a equal to delta beta a. That means propagation constant, how much it is being added because of the perturbation due to the second waveguide. Cool. Now another coupling strength, that is actually the term contribution coming from the second waveguide, how much energy or amplitude is being coupled contributing to waveguide A. Okay. This is the kappa AB, that is actually defined, if you see kappa AB here, EA star EB delta n square. We call this one something like that, evolution term of the guided mode A, evolution term of the guided mode A due to the contribution from EBXY. So, because of this field EBXY, that one, how much energy is being tunneled to mode in the propagating mode in the waveguide A, and vice versa is kappa BA. If you see their term, just A, B will be interchanged. A will become B here, this A will become B here, this B will become A here. So, this is how we can say that how energy mutually coupled energy. So, this contribute to dA dz, this part kappa AB, and kappa BA contributes to dB dz. So, once kappa AB present, obviously kappa BA will be present also. Okay, we will just discuss that. Normally, for identical waveguides, if waveguides are identical, then this thing EB EA star, they will be, their field distribution will be identical, and delta NA square and delta NB square will be identical. Only thing is that you have to see EA star EB star, that is changed only. So, normally kappa AB will be equal to kappa B star BA star, that can be considered as a kappa. So, for identical waveguide, this condition, if you see this, compare these two things, if waveguides are identical. So, mutually coupling strength from waveguide A to waveguide B and waveguide B to waveguide A, kappa AB and kappa B star, they are just complex conjugate. So, one coupling this side takes complex conjugate, and other side just, if you know one way, then other way, if that is coming as a complex, the other way will be just complex conjugate, that is it. And this one we have discussed here. So, now start from here, coupled equation. Keep in mind that kappa AA, kappa AB, kappa BB, kappa BA, they are known, they can be calculated using your normal Moore solver, okay, or you can use any other method to know that. Okay. In this case, it is known. Now, I would like to solve how is AZ and BZ evolving. If I know an analytical equation for AZ and BZ, then that is how we can call that the coupled differential equation is solved. So, towards that end, what we do? This is just, we take some trick. We just both sides we multiply by e to the power j kappa A. You will come to know why, it will be more and more clearer why we are doing so. And this side we are multiplying both sides e to the power j kappa BB. So, this is some trick to solve this differential equation. Okay. Then what I do? Here, if you see, these two terms can be written like this. How? You see, if I take this one, the first term to left hand side, then it will be like dA by dz plus j kappa AA AZ, right, AZ, and then you multiply j kappa AA here also e to the power j kappa AA. So, this you can get in a compact form d dz AZ e to the power j kappa AA. So, after multiplication both side, the first term if you take left hand side, that can be written in compact form. 2 z dependent function, if you just make a derivative, first one it will remain dA by dz e to the power j kappa AZ, and here also, okay, here it should be z, it should be z also if you are multiplying to the power j kappa AZ, that is a typo error. So, if you just multiply here, it is correctly multiplied here, then you are getting like this, and right hand side you also multiply a to the power j kappa AAZ. Okay. So, if you multiply that one, that is added here. So, you had a beta A minus beta B, that beta A beta B is there, in between I just put kappa A. I clubbed kappa A with beta A because you know this kappa A it will appear like a how much propagation constant is modulated in waveguide A. Similarly, here kappa BB z I am multiplying. So, I wrote same thing here in this form, and right hand side same kappa B A A z and e to the power minus j beta, and then kappa B B I have just clubbed with beta B, because beta B plus kappa B B, that means modified propagation constant because of the presence of your other waveguide. So far good. Now, I just do little bit simplification. So, this one simplifying, what I do, left hand side I kept as it is, right hand side what I did, I just multiplied e to the power j kappa B B z, and here I multiplied e to the power minus j kappa B B z. If you multiply this and this, it will be basically 1 together. So, this one I multiplied with B z, I kept clubbed here just to make some kind of A z, along with that e to the power j kappa A A, here B z e to the power j kappa B B I have kept. And this one if you multiply here, then you have beta A kappa A, and one more kappa B B will come, that can be clubbed with beta B kappa B B. So, that means instead of this one I now have modified beta A plus kappa A, beta B plus kappa B B. So, this can be written as beta A prime and this can be written as beta B prime, that is modified propagation constant because of the mutual interaction between the waveguides. Okay. So, same way I have also simplified here. What we did here? We have just multiplied e to the power j kappa A and e to the power minus j kappa A z. If you multiply these two, meaningless 1, as if you are multiplying 1, but this one I club with A z and this one I club with phasor, right. This simplification help us to consider further. Okay. You should not forget that e to the power k b b z is multiplied there. So, what we get here? I use this one as the A tilde z. Together this is a z function, right. Only thing is that as a function of z you have additional phase factor is there. So, I just club them together with a single z dependent modulation amplitude along with some kind of z dependent amplitude I just added here, I just consider here. And similarly, for B I will be writing this one as a B tilde like this. Okay. And one more thing I will be considering, this longitudinal phase factor whatever we are considering, that is defined by 2 delta. So, I will be using this one as a 2 delta here, instead of that 2 delta, instead of that 2 delta, and instead of that I will be putting A tilde z, and instead of that I will be putting B tilde z. Here I will be putting, but I should keep in mind how we have defined. Here I will be putting A tilde z and B tilde z, that is how we will be writing. Okay. So, it is straightforward, simple, just you have to use some kind of trick to get a suitable analytical solution. Okay. Now, what we do? Just once again I try to remind you, if they are identical waveguides, that means beta A equal to beta B equal to beta naught, kappa A B will be equal to this one, kappa B star will be this one, and delta beta naught, kappa A, kappa B B delta beta naught, and delta will be equal to 0. That means I can directly put this one equal to 1 because the exponential 0 is 1, here also it will be 1. So, our solution will be very simple, straightforward. I can write dA dz equal to minus j kappa A B B tilde z. So, that will be our simple exponential equation, sinusoidal solutions you will be getting, how it will be coming. But normally we want to consider dissimilar waveguide, non-identical waveguide. So, we will continue, but anytime if you want to see what is the solution for the identical waveguide, you have to just consider these things. That is it, that is the conceptual things. Now, so now we go, we simplify this one. this way, this one is delta, we have written j 2 delta z, this is actually 2 delta, we have considered phase factor here, put just simplification, and this one simplified like this. So, it is just identical equation. This type of identical coupled equation we have also seen earlier when co-propagating modes are coupled in the same waveguide, we have discussed earlier. So, but there also we have just solved up to this point, differential equation we have done, but we have not solved this differential equation. We derived this differential equation, but we have not solved this equation. But now we want to solve this equation. The solution method here, whatever we are using, that can be considered same for coupled mode equation when modes are guided in a single waveguide. Only thing is that here we have little bit modification of propagation constant like this, and there this two waveguide mode instead of beta A and beta B, I would be considering beta 1 and beta 2, both are in the same waveguide, how they are coupled. If some perturbation introduced and if they are coupling, the same type of differential equation we would be also treating. Okay. So, it is just so far we have shown that this coupled differential equation is in a between two waveguide modes is almost identical with the coupled differential equation between two modes in a perturbed waveguide, single perturbed waveguide. Okay. So, now we will be moving for solutions. I have just summarized whatever so far important thing we need. We need these two things for solutions, and we have to always keep in mind what is kappa AA, what is kappa AB, what is kappa BB, and what is kappa BA, and what are the parameter we have used. This is we can consider some kind of phase mismatch. This is the perturbed waveguide propagation constant for waveguide A, perturbed waveguide because of the presence of second waveguide, whatever the propagation constant, and since beta A not equal to beta B, kappa A, kappa BB, whatever it contributes, that also will not be, may not be they are equal. But after perturbation it can happen that 2 delta equal to 0, that can be considered. If you can design, that is fine. And we have considered A tilde z, that is instead of A z we have added one more kappa A z in that equation, that as a result you are getting this one and this one. So, straightforward, whatever we have discussed we have written. Now, again for identical waveguide you just put delta equal to 0, just to remind you. If you see, now we will just move on. We want to solve A tilde z or A z. Just if you solve this one, that means you will be directly getting A z also, right, because you know their relationship. Okay. So, A z and this one, how they are related, you know. So, what we do? We do second derivative of this one. Both side you do derivative with respect to z once more. Then first term will be this one, and second term you have this is also z dependent function, this is also z dependent function. So, we can define like that, minus j kappa b kappa a b db dz, and this one I kept, then I kept up to this one, and this one I will be making derivative. So, I will be getting j j minus 1 plus, so plus, so it is a real part 2 delta kappa a b, of course kappa a b complex, that can be considered, beta j can be complex, this is also complex. So, only j is not there, okay, j will be cancelled. So, you will be getting second term. Now, in this equation you see still it is coupled, you are getting second derivative of a, but you have first derivative of b and b is there. So, what we can do, I can take this one equal to this one, right hand side only a z, I can put here, and b I can b to the power this one, this value I can get from here and I can put down here. Then what I will be getting, this equation will be completely independent of b, it will be only a tilde dependent. So, that is what I have written. So, this one I have taken from here and this one I have taken from here, then I get this thing. So, dB instead of dB dz I have just put this one directly, and 2 delta kappa a b and b z, this one is equal 1 over minus j kappa a b dA tilde dz. So, this is straightforward, we just put here mathematically. Okay. So, it is a very simple. Now, again to proceed further, I think it would be better, because you have kappa a b that will be cancelled of course here, but here kappa a b and kappa b a, two terms are there. If they are different, you can keep on using that for solution, but for to get a complete analytical solutions, most of the time also practically you will see kappa AB will be equal to kappa star BA equal to kappa. If you just consider this concept, kappa AB equal to kappa B star, kappa BA star equal to kappa, and in substitute here the minus minus plus j j minus, and then kappa square it will be. So, this will be kappa, this will be kappa star. So, kappa square and minus minus plus j j minus. So, one more minus, if you take this side that will be plus, okay, and if you take this to this side that will be also minus. If you take j upward, this minus j you can cut, you can write j plus j here in the top. So, it will be plus j. So, if you take this side that will be minus. So, what we get? We get this equation. So, this term goes to like this, and this term goes like this, because this one cancel, e to the power minus j to delta z to delta and z. Delta is different, delta is defined by this one. Okay. So, this one will become this one. So, this one and this one. So, ultimately we get this equation, second order differential equation involving only A amplitude. Once we get solution A here, then I will be able to solve B from here. Just to make a derivative, I can relate what is the value of B. So, this now challenge is that how to solve this equation. Okay, let us move on. So, let us assume that the solution of the second order differential equation to solve this, I think normal method is that you just assume a solution, exponential solutions, and then use a substitute and get some constant, and that constant value is solved from the initial boundary condition. That is the standard way of second order differential equation, how you solve. So, you consider A tilde z equal to something r naught e to the power mz. If you substitute here, what you will get? Second order derivative you will be getting m square, and this first order derivative you will be getting m, and this one simply you will be getting this thing. So, you will be getting, after substituting here, you will be getting this equation to solve for m. So, if you solve this m, so you get m equal to minus b plus minus root over b square minus 4 ac by 2 standard way, and then you find m value is you are getting, it is of course complex. Yeah, here it will be this one, j will be common to both. So, because here minus sign, so this will be j also, here one will be j will be there, just type of mistake. Okay. So, in that case we will be just considering, here it is written, okay, delta plus minus s, this square root of kappa square and delta square whatever you are getting, that you are assuming that is equal to s square. They are positive value, kappa square plus delta square positive value, and square root whatever you are getting, or they are related by s square. Okay. So, basically s actually depend on kappa d actually in this square form. So, one axis kappa, another axis, so diagonally to be s. So, that way you can represent. Okay. Now, we know this is the solution we consider, and this m value can be two different value, that is actually imaginary complex. So, for this purpose, for this type of root, we can consider solution of this kind. Basically, I can consider say k1, the r1 we are considering r1 e to the power j delta plus s plus r2 e to the power j delta minus s. Okay. So, if you just a little bit modify, you can actually represent, because you see this is actually e to the power something j theta something like that, you can write cos theta plus j sin theta. So, in little bit simplify, we can introduce one more constant r1 and r2, and r1 cos s z, z of course, z is there. So, solutions you are considering, right, it is z. So, r1 cos s z, r2 sin s z you can consider, right. So, this is the solution I can consider, but we have introduced r1 and r2 that can be solved by using of initial condition. Okay. So, now once you know this one a z, I can just use this a z here and I can find b z. So, I have written here how you will be getting a z b z solutions. In this case, I have just considered that e to the power j k, this tilde whatever e to the power j kappa a, that term I have just ignored. Ultimately, you will be getting b z and a z. Okay. Whatever you get, along with that you are supposed to multiply e to the power j kappa a, and here it will be getting e to the power j kappa a, entire term you have to multiply kappa b b z and z, then you would be getting tilde. So, just factoring that one, you are getting these solutions here. Okay. So, ultimately we know that how they are related, but this type of solutions you can get also the coupled solution, coupled mode equation in single waveguide also, when waveguide is part of it, can be with a grating or so on. Now, okay, for identical waveguide, I just remind you that for identical waveguide, one more additional thing is that delta will be equal to 0, and I have introduced this s square. So, when delta is 0, then s will be equal to kappa, simply s will be equal to kappa, because simple kappa square actually mode of the kappa star, right, kappa square means mode kappa star. Yeah. So, now we have these two equation. Now, challenge is that we have to find out R1 and R2 value. Once we know R1 and R2 value, then our thing is solved. Okay. So, what we did? Let us consider initial condition like this. In waveguide A at z equal to 0, because you see this is z dependent waveguide, z propagating waveguide, this is also z propagating waveguide. When you are launching here something A0 amplitude, but here B0 equal to 0. Nothing I am just considering. Then I try to find out at z equal to 0, I will be putting Az will be equal to A0, and this will be z equal to 0, this will be z equal to 0. If I put, then what I will be getting? R1 equal to A0. So, simple R1 equal to A0 you will be getting. But when I am putting Bz equal to 0, B0, that means I will be putting 0 for z equal to 0, I will be putting z equal to 0, z equal to 0, and R1 of course A0 I am finding, R1 A0 I am finding, then I can find R2 expression will be like this. Simple, straightforward. You just have to consider this one. You are just launching in one of the waveguide, then you get the solution for the entire all the two constants. So, just introducing this two constant, I get Az will be equal to this one in this type of form, and Bz will be in this type of form I can write. This is the ultimate solution. So, only thing is that in this waveguide, what is unknown? Only unknown thing is that delta and kappa. Once you know delta and kappa is also known. So, delta kappa you can compute, delta also you can compute. So, once you know numerically you can compute. So, you know that how long, suppose z dependent, if it is propagating, then how this Az will be evolving, amplitude will be evolving and Bz will be evolving, you know. Whatever it will be evolving, you can also add that an additional phase kappa A Z also has to be multiplied, then that will give you some kind of complete things. But this kappa A you can club here actually, beta A plus kappa A, then only thing is that you have to solve only Az, here also Bz. So, kappa A means modified propagation constant. Whenever you are considering modified propagation constant, you just deal with Az, Bz, that is it. So, these are the solutions. So, we are almost done this solution. So, once we know that solution, so we can use this to design our directional coupler or with desired specification. Good. So, we have again written down everything whatever we have considered so far, coupled equation so far, assumption kappa A B equal to kappa B star B A star, and this is also assumed, and this is the initial condition assumed. That means, one of the waveguide you are launching, another waveguide is nothing is there at the beginning at z equal to 0. Then your solutions as it propagates, what would be the amplitude in the waveguide A and whatever the amplitude in the waveguide B you can get. So, now we just take help of this structure, this cartoon. This is actually a standard representation of a directional coupler. So, what is that? You have two waveguide here, input waveguide, here input 1, input 2. Initially, they are decoupled, far away, decoupled, and then you can slowly bend. This type of abrupt bending is not possible. If it is abrupt bending, lot of losses will be there, but waveguide, when you are designing waveguide, you can make it smooth. Then waveguide can be adiabatically smoothly coming towards waveguide 2. Same situation you can consider here, it is smoothly, slowly, without any loss, this mode can come here, this waveguide can come here. And then here also this can be smooth, this should not be kink or something like this, and this one also should be smooth, right, smooth. Okay. Here all this you just consider smooth, otherwise in the junction you will be getting, if it is not adiabatic, then you will be getting losses. So, something like this. So, this is your waveguide smooth, it is kind of S bend type structure, S bend type of structure you just make, so that you can get almost no loss, adiabatic. So, adiabatically both the waveguide come closer, and when you see that their evanescent tail is almost touching other one according to the gap, then you maintain this length parallel, make it parallel. So, this is the region you can start z equal to 0 and z equal to say L, L is the length. So, interacting length is L, and in the interacting length this L is basically waveguides are parallel. Actually, if you are if you want more complication because of the some kind of design fashion, so you can have this, one can be bent structure, another can be straight, something like this, one waveguide like this, another waveguide like this, it can be, but appropriately you have to model this one, so that you can analytically get good solutions. So, for the moment our intention is to find out a just comprehensive analytical solutions. So, we consider that okay, both the coupled waveguides are parallel, they can be fabricated easily of course. Now, I know that this is the two equations. If I have A naught, I am launching here one of the waveguide, then I know A z means here z equal to L, z equal to L. So, everywhere z equal to L if I put, then I will be getting whatever at the output of, this is actually called bar waveguide, and this is whenever you are launching with respect to this one, this would be called cross waveguide. Okay. In the bar, you know the expression will be here, once it is detached after L it will remain constant, assume that waveguides are lossless, and similarly here whatever it will be crossed coupled, that will be like this. Okay. So, this equation basically e to the minus j delta L. So, depending on the L you can find out what is the amplitude, and of course, A naught can be 1, A naught square can be 1 watt, it can be 1 milliwatt, it can be anything. So, if you know the amplitude here, then you know after interaction length of L and then decoupled, then whatever value it is coming out, how much amplitude will be there here, we know that. And then again it will be propagating like E A, E B, X Y, and then e to the power j omega t minus beta B z. So, that way it will be propagating, but this is the amplitude. Okay. After here. So, here will be, this will be amplitude and it will be multiplied by E A X Y, that is the profile, this one multiplied by e to the power j omega t minus beta A z. But whatever happening here, that actually decides your amplitude variation, because that is the interacting region. So, they exchange energy, that is why their amplitude is changed when they are decoupled. That is how we can derive using the coupled mode equation. Okay. So, this method actually very powerful to as a basis to have a compact model of any directional coupler you need for circuit simulation. Okay. Let us see what is the power, that means A naught square, whatever power, A naught as amplitude, A naught square I can consider as a corresponding power amplitude. So, this is entire amplitude, it is normally we have assumed, we have normalized our mode profile such that the amplitudes is actually carrying all the power expression. So, A naught square, this is a P input. So, if it is P input, then output side, this is the coupled or cross port, P C here, whatever I will be getting here, right, how much I will be getting there. So, what I will be doing, this is the amplitude, you take complex conjugate of this one, that will be your, and multiply with this one, that will be your coupled power. If you take complex conjugate of this one, then you will be getting A j delta L e to the power j delta L, and that will be j capacitor by S sin SL, that is the complex conjugate multiplied by A naught. So, this one and you multiply with this one, e to the power j delta L, this phase information will be cancelled, j k minus j k, that means it will be j j minus, so it will be k k star, basically k square, kappa, not k, should be kappa, kappa square. So, numerator will be kappa square and denominator will be one s is here, another s is here, complex conjugate you multiply. So, s square means, we know s square means kappa square delta square. So, this would be your kappa square delta square and sin SL, that will be sin square SL. So, sin square S means this one, L is this one, and A naught square means P input. So, if this is the P input, cross port power will be expressed by this one. So, I know how much power is coupled. So, power splitting you can find out. So, this is interesting, this is the expression, important expression, that if you have two non-identical waveguide having some kind of delta is there, if they are non-identical, this delta will be non-zero and you will be getting this expression. Now, we just little bit analyze this thing. What would be the maximum power here? How that this value, you see this is sin square. So, that will be varying if you increase your length. So, depending on the length, this value will be going sin square function. This is a constant for a parallel waveguide, kappa square, delta square, they can be whatever the parameter, this is a constant. So, the power coupled in the cross port, that is actually varying as a sin square with P in. So, I can say that if L equal to pi by 2 n plus 1 pi by 2 divided by this kappa square plus delta square. So, if your L value, n is integer, L value is this one, maybe 2 we can write here, okay, 2n plus 1 pi divided by this one, then you know the sin square value will be 1, n equal to 0, 1, 2, 3, 4, so on. That means odd integer multiple of pi by 2, this one, that will be cancelled. So, it will be 1. So, normally in the cross port I can see that power is varying maximum and then reducing, maximum and then it is reducing according to the sin square function. So, it will be just, if you just as a function of length, if you just plot, it will go up to some maximum value and then comes back according to the sines, then again go maximum value and comes back, again goes maximum value and comes back. And if you see what is this maximum value? So, sin square value this much, for any integer value of pi by 2, if you just use, that will be 1. So, what would be maximum value? This would be your maximum value. So, that is what we have written. In the cross port, maximum power coupled can be this one, depending on the input. You can take a ratio, that can be transfer function of the maximum value. So, you can design your L such that this L equal to this multiplied by pi by 2, okay, that according this entire thing should be coming as a pi by 2 times 2n plus 1, such that that particular length can ensure your maximum coupling, but that maximum coupling is how much? This one. Just note that delta square is a positive value, kappa square plus delta square. So, it will be never equal to P input as long as delta not equal to 0. If delta not equal to 0, that means you will never be able to transfer complete power launched into directional coupler can be cross coupled to the second waveguide, cannot be appeared in the cross port. So, if this is important conclusion, that if your waveguides are not identical, you will never be able to transfer complete power to the second waveguide. Whatever length you increase, it will go up to a certain value, this one according to the delta, this value, but it will never become P input. Whenever it is coming down, that means power is going back to bar port again. So, you can plot basically as a function of delta or as a function of length how power is actually transferring from input to output cross port. If you are considering no other losses are there, only waveguide, whenever some power is lost by one waveguide, that will be gained by another waveguide. If that is the condition, okay, some loss, additional loss will be there, that can be treated separately, individually you can consider that thing. So, in this case we can say that the PC max, for example, identical waveguides, if you are just considering, just take delta equal to 0. So, if delta equal to 0, if you just put here in the previous slide, delta equal to 0, if you see, this will be kappa L, and this will be delta equal to 0, kappa square 1. So, that means it is basically sine square kappa L P input, that is what the sine square kappa L P input, that is the power coupled in the cross port. So, if you see, now you see L, if you are just changing, kappa L can be pi by 2, can be 3 pi by 2, can be 5 pi by 2 and so on. So, for those lengths actually you will be getting power completely transferred to the second waveguide. So, for identical waveguide you can indeed transfer power to the second waveguide completely, okay, theory says. And obviously, if it is lossless, whatever it is coupled to the second waveguide, whatever will be there in the bar port PB, that means 1 minus sine square kappa L P input. Okay. This is obviously this will be less than 1, right. So, together PB plus PC should be equal to P input, lossless. So, power splitting will be distributed like that, and in that case maximum power coupling to the cross port obviously equal to P input. So, in this case power completely transferred to the second waveguide, in that case in the bar port 0 power, and if you keep on increasing the length, you can reach to another length when power will be coupled back to the again bar port. So, it is actually varying with a sine function, sine square function or cosine square function. In this case sine square function is better representation. Okay. Good. Now let us go for a, we are now done how to solve and how to design the waveguide. Obviously if you see that if you want a 3 dB power splitter, kappa L it should be pi by 4, kappa L should be pi by 4. If it is pi by 4, that means sine kappa L equal to 1 by root 2 and sine square will be half. So, it will be 50% here and 50% here. So, you can design kappa L equal to pi by 4 or L 3 dB equal to pi by 4 kappa. So, if you calculate kappa value, if you know what is the kappa value, you will be able to calculate what is the 3 dB length. So, this kappa value depends on what is the gap. Kappa expression we know that kappa means it is basically we consider kappa AB or kappa BA, that expression. So, that expression depends on how closely these two fields are overlapped. So, more the kappa value you can make compact, more the kappa value you can make length smaller, compact length of 3 dB power splitter if you want. So, you do not need Y junction basically. Y junction designing, adiabatic design is very difficult, rather adiabatic design of directional coupler is relatively easier. This is only because of it is a waveguide is basically very tightly confined mode and little bit perturbation etc. if it is there, then you can get lot of losses. So, directional coupler is preferred most, and that is why this is an important power splitter or amplitude splitter used for photonic integrated circuits. Now, we are going for formulation of the transfer matrix. Okay. I again repeat, what is the amplitude? Whenever you are launching here, you can get bar port amplitude, and this is your cross port amplitude. We represent A naught, and here we are writing A1 and B1. Okay. So, a second waveguide any amplitude we are considering like a B, and first waveguide any amplitude we are considering, you remember that we are just considering AZ and BZ. So, that is the reason I am considering A1 and B1 here, and that is what is written here, right. L length, that is why L we have put here. So, according to the coupled mode equation, whatever we get, that is what we have written. Now, you see, if I try to get a transfer matrix, how it will be looking like? I have only one input and I can have a row matrix. So, this is the value I have put first element and this is the second element. Okay. So, we can write A1 B1 something like this. Okay. A1 will be this one multiplied by A naught and B1 will be this one multiplied by A naught. That is in the matrix form we can write. And if delta equal to 0, then it will be cos kappa L this one. So, any time at any length if you see that the value in the this one actually in the cross port, right, because delta equal to 0 means this term will go and S will become kappa, right. So, in that case total value will be cos square kappa L and this one will be kappa kappa will be cancelled, complex conjugate if you take sin square kappa L. So, that should be equal to 1. Normally if that is equal to 1, that means whatever power you are launching here you will be getting, even delta equal to 0 you can solve, even delta not equal to 0 also, if you just take complex conjugate multiply and complex conjugate multiply, add them together, then you will get A naught square here, whatever power is coming, it is a lossless solution. Now, if you have a B naught, this waveguide, first waveguide port 1, you are launching A naught, you got this one and you got this one. Now, you have B naught, then you see whatever you supposed to get in the cross, because of the B naught, here you will be getting almost similar. So, here you are getting this one, now because of B naught you will be getting similar thing in the cross port here, plus A1 will be adding this one and B1 will be adding another type of this type of solutions here. So, this kind of superposition principle, you just consider B naught, you just stop, then you see whatever value you are getting. Now, A naught stop, you see the B naught, whatever value you are getting, and then total value, if both are on, switch on, then superposition. It is in electrical circuit, normally we use that, even for KCL, KVL, all these things, superposition principle we use. So, here also this same superposition principle we are using. Okay. Now, if I just try to make a matrix form, this is because A naught B naught is the input, A1 B1 is the output, A naught B naught is the output. I want A1 B1, that is this thing, and some matrix form I will write, so that I can get A naught B naught. That is what you need for circuit simulation. So, from this equation we can just simply write, this is the A1 component and this is coming from B naught. So, A1 will be this one multiplied by A naught plus this one multiplied by this one, and B1 will be this one multiplied by A naught, this one multiplied by B naught. So, that is what this thing together, these two equation together we can write in a matrix form. So far it is good, but little bit modification required, this thing, this needs some modification. Why? Clarify. So, whatever we have just so far discussed, directly we are getting, this is good. Now, if you just think to satisfy time reversal symmetry. So, you see all these elements are complex. Now, we are launching from this side and this side. It can happen that we are launching this side A1 and B1 and I should be able to get A naught and B naught from the same matrix, right. This I have to take inverse to this side and I should be able to get. So, to get this one correctly, that this is basically bidirectional device. I am launching this side, whatever I am getting this one, if I launch this side, there also I should be getting identical mathematical matrix formulation we need. So, for that purpose what we do, we just decompose this one, we write here as it is, okay, and this one I use the complex conjugate. You see e to the power j delta L, I will be writing minus e to the power j delta L. S I am considering like a real cos SL, because SS square, you see if we have defined this one, that is a positive number, I just consider real, and then this minus j plus j complex conjugate I am writing delta by S, right. Delta is a real number we consider, and in this term I consider this minus j I just keep separated, without minus j here and without minus j here, rest of the time thing I can consider complex conjugate. Why this minus j I am not counting, I will be discussing that. Okay. Now we consider the minus jk, I just consider minus j I consider kappa here kappa star, this one I am just converted into kappa star, and e to the minus j delta L, e to the power j delta L. Okay. So, if it is the case, if this is the situation, this type of equation, if you just see other than this minus j, if you just take complex conjugate, then you will be getting complex conjugate and then transpose, that will be actually inverse. So, you will be getting same, other than minus j complex conjugate, minus j you have to just multiply diagonally. Then this one complex conjugate if you take and transpose, that will be actually inverse. So, I will be getting A naught B naught in terms of A1 B1. So, that is the reason for to satisfy time reversal symmetry, we will be just using this matrix in this form, and in this form if you write one additional thing you will be getting. What is that? You see, you are just representing this one, this is the same thing we have kept from before, but we can write minus j I have kept, and then t star and r star I am considering, where r is this one, t is this one. If you just use this form, if you just take the determinant of this one r star, and you will be getting plus t star, right, that is the determinant, and that determinant you have to have 1 if it is a lossless waveguide, right, r square. So, determinant is actually equal to r square plus t square, if it is lossless this should be equal to 1. So, that is why it is actually unitary matrix, determinant is 1. So, for lossless case, if it is loss is there also, you just consider everything is propagative, total length is the e to the power minus alpha L you can consider. Just ignoring loss, practical situation loss will be there, that can be considered separately. Otherwise, you can just simply consider this type of device as a unitary operation, unitary transfer function, unitary, there is no loss. So, this type of unitary transfer, transfer operation, that is very useful also quantum mechanical functions we will see later. Okay. So, this is actually your ultimate transfer function, transfer matrix of a directional coupler. You should keep in mind that r is defined like this and t will be defined like that. Whatever value r, put here, r star put here, t whatever you put here, t star if you put here, then this will be your transfer matrix for the directional coupler. Any directional coupler you design and you can represent, once you can, this can be calculated, you know, delta is known, s can be calculated, everything can be calculated in complex form, it can be represented, and then you can use that as a compact model, compact transfer matrix for the directional coupler. Okay. Now, this is in summary. So, this is the complete transfer function, this is your input, this is your output, A1, B1 you will be getting when you know A naught, B naught, but this is your like a black box you can use directional coupler. If you know R and T, right. So, then you can get, this is something input here, you get 2 output ports here. So, input to output transfer function can be represented, this whatever we have discussed, this is repeated here. Okay. Repeated here, just to discuss one more thing, just for identical waveguide, you know delta equal to 0, s equal to kappa, delta equal to 0, s equal to kappa if you put cos kappa L, this one and this one. So, that means here you will be getting cos kappa L for identical waveguide and into A naught plus you will be getting, plus means minus j kappa by kappa sin kappa L. So, one thing you should remember that, suppose kappa is real. So, anything you are getting, this is for B naught, right, and anything you are launching here and whatever you are getting here, you have a minus j here, and whenever it is going from this to this also you have a minus j additional thing here, that is coming from the physics of the directional coupler. When it is cross coupling, you will have this minus j, means e to the power minus j pi by 2 phase shift, pi by 2 phase shift always will be there. When it is tunneled through directional coupler to the other waveguide, then if you see the this to this is your transfer function from input to bar port. This is your transfer function from input to cross port. So, input to cross port always you are adding minus j, that is coming because of the theory of coupled mode equation, theory of directional coupler, where anything you couple to the second waveguide you get pi by 2 phase shift, e to the minus j pi by 2. That is unlikely in Y junction, you know, you remember that whenever you are launching this one, whatever you are getting here and whatever you are getting here, they are actually same phase. But here you see light is going directly, another is just crossing. Once it is crossing, phase shift is pi by 2. Okay. That is actually inclusively used here in this equation, it is inclusively used. If this is a general equation, basically transfer matrix for the coupled directional coupler. Okay. So, this is from here onward we will be just discussing forward. For many other device complicated structures, complex circuit, but this directional coupler is actually basic building block, and we can take help of this structure to understand other component like Mach Zehnder interferometer also made out of. As I said that this directional coupler is fabrication friendly for silicon on insulator platform rather than Y junction. So, we will be using this directional coupler for demonstrating Mach Zehnder interferometer again instead of Y junction, and because Y junction transfer matrix is different, directional coupler transfer matrix is different. So, you can use this one for understanding Mach Zehnder interferometer output. You can again use this thing for finding out the transfer function of Mach Zehnder interferometer, transfer function of ring resonator and so on. Okay. With this I stop today, we will wait for the next lectures. Thank you very much.